Okay, let's wrap up lasers with some applications. And so, some of the applications, which are no longer as popular now, are CD, DVD, and Blu-ray. When they basically record data off these discs, they shine laser spots onto pits or reflective areas, and whether or not you get reflection, a pit would be no reflection, and a smooth area would be reflection. You get a 1 or a 0 in terms of the digital bit written into the disc. And so one of the big things with lasers is over time they've moved to shorter wavelengths, longer, shorter, and even shorter wavelengths, which allows them to basically focus the light down to smaller features. Smaller wavelength can see smaller features, and they, for example, Blu-ray discs, they use 405 nanometer light, which gives them huge capacities compared to something like a CD or DVD. Now, let's focus on telecommunications. If we want to do telecommunications, we need to modulate the lasers. And lasers absolutely dominate in high-speed data generation that we see with the internet. And so how are you going to modulate a laser? Well, what you're going to do is I'll put my laser here, and I'll have a waveguide with 2 arms here. So I'll split 50% of the power down each arm. Now remember like we talked about before, the velocity of light is the speed of light divided by the refractive index. The wavelength gets shorter and the speed slows down based on the refractive index. Okay? So, what we can do is, again, we can use a PN junction on this arm here to inject carriers, which raises the refractive index on this arm, which slows the light down according to the speed of light divided by n. And if it slows the light down, then it can show up on this end out of phase with the light coming through this arm. And so if things are out of phase, again, if I have 2 photons in phase, I send 1 photon, this one, this one, and this is my output. The resultant of those 2 photons will be a larger optical power observed. But if I make this 180 degrees out of phase by delaying this, by raising the refractive index, the phases, out of phases, add up and you see no optical power at the output. So I can basically modulate this diode very quickly in terms of changing its refractive index to basically turn the output into 0s and 1s, if I were looking at an output pulse, coming out like this, where I have basically 1, 0, 1, 0, 0, 1, etc. So I could generate an optical pulse by feeding that same data in terms of voltages into this PN junction here. If you make this long enough, you don't need a huge change in refractive index, and if you want to calculate how the refractive index changes as a function of doping or injected carriers, this equation allows you to do that. Here's the actual device, here's the waveguide, here's the P-type region, P-type, P-type, and N-type. So here's my PN junction where I forward bias it and inject carriers to raise refractive index. Here's my control electrodes on top here. And one of the key things about this is that you'll notice that they call this traveling wave electrodes. Well, that means that this is a microwave transmission line. The reason why they need that is that these electrodes are being modulated so quickly that if you're going to get that RF signal to get to this diode, you need to have specially designed transmission line for maximum forward propagation of the electrical signal. Hence why they call it traveling wave electrodes. So if I want to make this work well, typically I'll design the laser material such that it has a long recombination. So my laser over here feeding light in will have a long recombination lifetime, which gives me efficient lasing. And then by putting the PN junction out here, I can design this PN junction in the waveguide for fast recombination, meaning that if I forward bias this and build a bunch of excess carriers, raise the refractive index, as soon as I stop forward biasing it, the carriers will recombine and I will lose the refractive index change, so I can generate my 1s and 0s on this. The thing you might be asking is, well, why don't I just modulate the laser itself? Well, the reason why you don't modulate the laser itself is, again, the laser was designed for long recombination lifetime for efficient lasing, meaning that if you're trying to turn the laser off, the optical output wouldn't go away right away because your carrier population remains there for a certain period of time. And so this allows me to design an efficient laser for maximum lasing efficiency, and then design a separate part of a PN junction for fast recombination to be switched as quickly as possible. How do I transport the data once I've created it? Well, you use an optical fiber, which has a jacket, a polymer layer, a cladding, and a core. The core, shown here, has higher refractive index than the cladding, so if this is the index profile, low index, higher index, and as a result, you get total internal reflection at the interface from high to low index of refraction. And just like that, those dielectric mirrors we had before, the beauty of this is there's no optical loss. If I used a metal here, I'd have some optical loss, right? So by using dielectric materials, in this case silicon dioxide, with change to have a little bit higher refracted index in the middle, lower on the outside, I get total internal reflection, which has no optical loss whatsoever and allows efficient data transmission. How do they make these fibers? Well, they typically take a preform, which is like this, which can be several centimeters wide. They put it at the top of a tower, they heat it up, it melts, they draw it down, and draw it into a tiny fiber by the time it gets to the bottom. So, what type of material do we use for optical fibers? Well, it's interesting to note that we use the same type of material that we use for computing, except it's oxidized. So you use silicon dioxide for optical fibers. The reason why is if you look at attenuation versus wavelength, silicon dioxide has very low attenuation at 1.5 microns and around 1.3 microns as well. And it's also very abundant. So it's this material with very low optical loss. In this case, it's about 0.3 dB, which is very low, per kilometer. 0.3 dB per kilometer. So that's only 50% loss per kilometer. If I calculate how far I could go to get to 10% optical power, we've seen this calculation before. I'll do the math here and I'll solve for Z, and I get 30,000 meters before I get down to 10% of my original optical power in terms of attenuation. So that's substantial. So the question is, how far can you go? What's the data rate limitation? Well, eventually, 30 kilometers is still an issue, because if I want to go and send light across the Pacific Ocean in terms of optical fiber communications between the US and Asia, it's a lot farther than 30 kilometers in between there. And so at some point I have to re-amplify the data going down these fibers. So here's one way you could do it. You could basically say, here's my signal coming in, I have a PN junction photodetector, I have a circuit that would regenerate the digital pulse because it comes in a little bit noisy by the time it gets there. And then I would have a laser here which I would modulate again with that split waveguide, and I get my new data out that's nice and amplified and clean. But what's the problem with this? Well, the problem with this is that this does not occur at the speed of light, right? There is always delays in electronics. So I would rather have something, if I already have my data traveling down a fiber at the speed of light, I would rather have something that amplifies at the speed of light. The other thing, this requires a lot of circuitry and electrical power, so there has to be a simpler way to do this, and there is. And so how do you amplify it? You've got two options. We could go back and use that semiconductor optical amplifier, right? Put a fiber at one end, so if this is my semiconductor optical amplifier here, and I bias it up, right? I could put a fiber at one end, a fiber at the other end, and basically I could have one photon come in, and I would get multiple photons being amplified out the other side. And the beauty of this is that it will occur at the speed of light. Light travels through here, and there's no delay like I would have with the electronics, and it's very simple. I just put one semiconductor optical amplifier here instead of all that circuitry I was showing in the previous slide. Now that's used for short haul, for example, local area amplification like in your neighborhood. If you're using Time Warner Phi optics, signal comes in, they amplify it and send it out to all the homes. They can do it with semiconductor optical amplifiers. For long haul across the Pacific Ocean or Atlantic Ocean or between cities, and the highest performance, you use a fiber amplifier. Unlike semiconductor optical amplifiers, there are no currents and there's less noise. What you do is you take a fiber and you dope it with erbium for amplifying 1.5 micron light or praseodymium for 1.3 microns. Those are those two minimum attenuations for silicon dioxide. So those are the two dominant telecom wavelengths. Let's focus on erbium. So if I'm having a laser which generates 1.5 micron light, I modulate it, then I want to use this to amplify it. What I do is I take my erbium atoms inside the fiber, I excite it up with a pump wavelength, typically 980 nanometers. These are the energy levels in erbium. Excite to this level, it radiates down, and then you'll see that electron sits at this level. If I bring in a photon, it can cause stimulated emission because the energy difference between these two is 1530 nanometers, so I can amplify 1530 nanometer light, which is 1.5 microns. This is just like electron-hole pairs, but it's with an atom energy levels in an atom, and you can still get stimulated emission the same way. So I just let this sit here until a photon comes along, and then I get stimulated emission. How you do this in a fiber is, here's my special fiber. You can see it here. I couple in the pump laser, which is 980 nanometers, which excites the erbium to this level. It relaxes down, gives off heat to get to this level. It just sits here until a photon comes along. Here's my fiber amplifier. I have a filter at the end that any of the pump laser, the 980, doesn't go on. This gets filtered out here. So again, the advantage is I've got amplification at the speed of light using just a special fiber and a diode laser to pump it and excite it. Don't get confused about laser types. You know, we've talked about laser diodes here. Gas lasers are very common, and those are not laser diodes. So helium neon laser, which is a conventional red laser you see very often, it's fairly large, but it's based on light emission from a gas which is excited. I won't go into the details. If you want to learn more details, you can take my optics course again next year. If you look at a helium neon laser or even a semiconductor laser, the emission wavelength looks like this. Remember when we did LEDs? If I had a red LED, the emission wavelength would look like this. It would be very broad, right? And then when you get a laser, it's this very narrow peak. Why is that? Well, the reason why, remember, is that all the light has to be in phase. And so in this case, here's the mirrors. And so there's only one wavelength which really fits the resonant mode for this laser. That wavelength dominates, and then you get a very narrow emission, because all this other emission that you could have for a red LED when you make it into a laser goes away because they're not at the resonant wavelength designed for the cavity between the mirrors. Again, this is a gas laser here, but the similar thing applies with the resonant cavity and a certain wavelength dominating. Also not a laser diode, solid state and fiber lasers are optically pumped. So it's like that fiber, erbium doped fiber amplifier, but you put mirrors and you get a laser. Example, industrial welding, they take an optical fiber, they dope it with ytterbium, which is the optically active atom that gives you the amplification, and they excite it with light, and they can find that they can get outputs of 3 to 10 kilowatts of optical power in the infrared. And so that's how they make these really high power industrial lasers. In terms of lasers that are being used in products you see around us you might not expect, BMW's most recent car uses lasers for the headlights, and it's not like you think. Basically, you're thinking that the lasers shoot out of the headlights. What they do is they actually use the laser, like if here's my headlight, let's say that this is my bulb, okay? So here's my bulb, and we'll just draw it like a conventional bulb here, and I want light emission to come out this way. The laser sits here. It basically hits a phosphor here. Here's a reflector. The phosphor converts the blue laser to partially to yellow, and so what I end up getting out is I get a white light out, which I'll just draw in black, hits this special reflector, which is a parabolic reflector, and then I get all my light out. So why not just basically use a blue LED to excite the phosphor? Well, it turns out that when you go to really high power lamps, lasers become more efficient than LEDs because they send the light out in a certain direction. As we know, all the photons go in the right direction, which is the right direction to excite a phosphor and get light emission out of this bulb. So when it comes to really bright bulbs like you need for the headlamps of a car, we might see lasers beating out LEDs because of their higher potential efficiency specific to this type of application. So at that point, this wraps up lasers, and we can finish up and you should be able to answer these review questions, and then we'll move on to one more lecture to finish off the course.